Hi everyone, following is my conversation with Chris Rakakos, VP of Modeling and Simulation at Julia Hub and research affiliate at MIT. We'll be talking about scientific AI and Julia. Hope you enjoy it. Chris, could you explain us what scientific machine learning is in general, like if we were 10?
Yeah, so scientific machine learning is the combination of prior scientific knowledge with machine learning, right? So machine learning is this whole kind of thing that's been developing recently where you say, oh, everything learns of itself, everything learns from data, right? But there's nothing about standard machine learning that says that, oh, you should have conservation of matter, you should have conservation of energy. Newton's laws is true or approximately true, or general relativity is true, right? And so what we're doing with scientific machine learning is building new kinds of algorithms that start from knowing what we already know about science and then saying, okay, now here's the data of new things. Tell us what we didn't know about in science, right? So it's this kind of mixture between what you would think of as, a physicist doing their physical modeling and this new machine learning world of learn everything from data.
Who is responsible for scientific machine learning? So any separate teams, engineers, who is it?
Yeah, so there's a lot of different groups doing it from different perspectives, right? I'd say that there is one group that is coming from the machine learning perspective, and of course, one group coming from the scientific modeling perspective, right? And they kind of have a bit of a different feel to it. So you have a lot of people coming from the computational science perspective where they're not as much physicists, they're more in the machine learning aspects, but they realize that there are some things that we need to include in our models that are not just pure neural network, right? So you have some things like physics informed neural networks and Fourier neural operators, which is kind of growing out of that domain. You have another group of folks which are if machine learning wasn't here today, they would just be doing standard physics, right? And I'm kind of in that group along with some other people who come more from physical modeling, biophysics, and from the engineering domains as well. So not really the computer science background per se, and incorporating machine learning into the work. And I think that there are slightly different methods there as well. There's kind of focus on things like universal differential equations and things, though there's kind of what we've seen is that these two methods or these two groups of methods are somewhat different, they're really trying to address the same problem. And so as a community, it's really come together that these different folks from what would be have never seen each other at conferences or work related things before now are coming together and saying, hey, look, we're actually looking at the same problem now. And so we kind of have a convergence of different domains really hitting with different people bringing different expertise.
Okay, great. So this is a really interdisciplinary team. I would sum it up.
Yeah, I mean, it's very interdisciplinary because some folks, are much more comfortable in machine learning and they're like, okay, I want to put, some folks are a lot of machine learning and they say, I want to put a little bit of physics into it. And then you have other folks who are like, I'm really big in physics, I want to put some machine learning into it, right? So it's really meeting in the middle then, but you can then see this different flavors of the different mixtures and with some more machine learning, some less machine learning as people are approaching this.
Do we need, let's say, much computing power for making scientific breakthroughs with machine learning? Do we need ever bigger models, or can we do it with relatively small models and using not so many GPUs?
I don't think that we need huge models for this, right? I mean, so for a lot of things that we've been looking, I mean, this is one of the keys behind scientific machine learning, right? When you use enough prior information, you don't need as much data, right? So we do a lot of our things with, 20 data points, 30 data points. And I mean, that's kind of a requirement. So I think that there's again, thinking about these two different perspectives, right? You have one camp, the camp that's really come at it from, hey, I do mathematical modeling and I want to incorporate some machine learning in. In this camp, they're really looking at it from the perspective of how can I use scientific machine learning as a way to augment models I already have. Right. So if I have a chemical reaction system, can I learn what chemical reaction I didn't know about that's required to complete my predictions, right? And in that kind of case, you can be very conservative on the size of the machine learning that you're doing. There is another camp that is looking at using machine learning starting from the machine learning aspect and bringing in some physical elements, even then what they're showing is that, hey, we can do machine learning in a way that is less data intensive than methods that are purely data driven, right? So in a sense, I mean, it's a bit hard to kind of pin down because, the general idea is that, you need a certain amount of information to make a good prediction. Information can come from prior information and models, or it can come from data. And so, as long as you can add the two together enough, if you have this much information, you make a good prediction, right? And the question really then becomes, well, do you have enough prior information to make it so that way your small amount of data is sufficient, right? And a lot of what people are doing in scientific machine learning is finding out ways to make our prior scientific knowledge go further, right? More conservation laws encoded, more things about, general relativity in there, symplectic manifolds, all these things that people do. Basically, if it's seen as a topic in physics, if someone, if you hear like, oh, gauge theory or something, right? Someone is trying to find out how to make a neural network that is, a gauge theory respecting neural network, and then showing that it's going to use less data. So since scientific machine learning is only a few years in, it's hard to really know at this point, like, oh, can we get away with, 30 data points or 50 data points for a new breakthrough? Or is it 300? Is it 3,000? We don't really know, because as we improve the amount of information that we can make use of, the amount goes down. But then also we'll be looking at harder problems. So it's a bit hard to balance, but it is at least a lot less. It's definitely not like the Google scale of, oh, hey, let's send up 3 billion satellites, and get the data to train machine learning. It's definitely not that case.
I've just watched a very good interview of Lex Friedman with Demis Hassabis. And Demis Hassabis says that, let's say, that all of research, in his opinion, in the future is on the intersection of various walks of science, of various disciplines of science. So science gets more and more multidisciplinary. And would you agree with that? And second question would be, with so much knowledge on the internet that generative models are running on, are new Nobel Prizes already on the internet? It's just, for the machines to pick this knowledge up.
Let's see. For the second one, I'll punt on the second one for now. I think that the answer is yes and no. There's probably some things that we don't know that's already in our databases, especially for things like drug development for protein information and such, right? People, I think, have that people are building these really large scale machine learning things, either academically, or you have companies like Schrodinger, which are mining things like the protein database, right, PDB, and finding that, hey, we probably have enough information to guess the protein structure here and know what it would bind to and what it wouldn't bind to, and these predictions are pretty accurate, right? So there is a lot of information on the web, especially with a lot of these open databases, a lot, especially in like, biology for sure. I mean, there's so many different transcriptomic databases, and I mean, it's same with astronomy, that people, even if we didn't have, if all government funding of all experiments stopped and we just had, the next 30 years of just analyzing the data, we probably still wouldn't get through everything we can learn from it. But I mean, that's not a reason to not do any more experiments, though, right? That just means that there's a lot of room for computational folk to be able to do what they're doing without having to wait on anybody, which I think is a good place to be in for science. What was the first question again? I think
the first question was, let's say, is science getting more and more multidisciplinary? So it's more and more all about, intertwining various disciplines of science and various scientific research, and at the end, various scientists.
Yeah, I think that, there's an interesting question going on here. I think that the way to describe it is really, so I went back to my old PhD program just a few weeks ago, right? Because I'm on the committee for changing the curriculum, right? And the PhD program that I was at was actually, it was a mathematical computational systems biology one, right? So I came to scientific machine learning. They're doing mathematics for understanding biology, which of course is a really messy system. And so people are trying to find what whatever they can to find out what is like the physics of biology, right? So theoretical biology is kind of this big place where model building happens every day because you don't have great models today, right? Well, scratch that. I mean, there are some decent models here and there, but you don't have a general model, like you have like general relativity, right? And so one of the things that's been interesting in this discussion is they say, okay, it's clear that machine learning is growing in popularity. So we definitely need to add things like machine learning to what someone who is a scientist in, mathematical systems biology is doing. But what do you drop, right? Because if you're going to put more things in the curriculum, you have to drop something out. And I think that this is where you really start to see why the world has to become multidisciplinary, and everyone has to be working with each other, because there was a time back when, back in yonder times, right, when it would be like, okay, if you learn enough calculus, if you learn enough calculus, you now kind of know the main tools everyone's using and go forward with it, right? But in today's times, what you're really saying is, okay, if we want someone to be a computational biologist, what do they need to learn that is not the biology? Well, they need to, of course, know how to code, right? They need to know software development practices and how to use Git and everything, right? Oh, obviously, they need to learn differential equations and numerical differential equations. Obviously, they need to do partial differential equations. Obviously. If we write out the whole list of obviously, they actually are doing a whole math PhD or a computational science PhD, right? And they won't even get to the biology yet. And so, like, it's at a certain point, you have to be like, obviously they need to be conversant in this, but they don't have to, but we can't expect everyone to do everything, right? We're beyond that point in the world of science. And so I think that, a lot of people are kind of taking it as given. They're just saying, oh, the next generation of scientists will all be, will all have taken a year of machine learning. Don't think you can take that as a given, because I mean, I've sat there in these committees to come up with curriculum, and I can tell you that, if you're going to add in a year of machine learning, you're also taking out a year of biology. And how much biology, how much of a biologist is someone if they've only ever done 2 courses in their 5 years, right? Like, and so, so I think that, where we're heading to as a scientific community is that I think everyone will have to do at least a little bit of coding and maybe understand how machine learning is useful and what some of the drawbacks are and everything. But I think that some of the folks that are saying like, oh, everyone's going to be star coder and a machine learning, I think that's just impractical. Looking at what it takes to be a biologist, looking at what it takes to be a biomedical engineer, looking at what it takes to be a mechanical engineer, right? There's an entire course load in those aspects alone. And so anyone who's being trained today will have to be conversant in coding and, be able to use little scripts and stuff. But there's a place for someone who is specialized in being very good at coding, and there's a space for someone who's being very specialized in the mathematics and specialized in machine learning, working with someone who's very specialized in the biology and such. And I think that means, okay, if we want to solve these problems that require machine learning and biology, you need a team. I mean, there's kind of no way around that. You need someone who has spent many years understanding how to do the experiments, and you need someone who understands the machine learning to know, if I do this machine learning on these experiments, will it be biased? Is it taking into account the noise, etc.? I mean, every once in a while, you're going to have some star people from some star programs that, will be able to kind of do both very well, but the average scientist won't. And so it will be interdisciplinary teams. And I think that's, we walked out of that curriculum change thing, kind of disheartened that we know that we cannot train everyone to do everything, but, kind of clear in the idea that this is going to have to be what the future looks like.
Being academic teacher, you see people, coming from high schools, right? I mean, you are you teach at one of the most prestigious universities in the world, which is MIT. But anyway, do you still you have, let's say, some overview of various schools and of the educational system? Does educational system prepare us for this kind of a model where people are complementary to one another?
I think it does. I mean, I think that, I kind of think that, there's a lot of downsides to some elementary and high school systems, to the way that they're kind of, not rigorous enough, maybe not enough math, not enough programming, right? There's a lot that you can throw out there. But in the end, I actually kind of find that, really trying to drive people to learn this stuff earlier, I don't think it's as helpful as just helping people learn how to be conversant, right? And be able to talk to other individuals well. I mean, one of the big things I did in high school was I was a drama kid. I did drama for 8 years. And, I would say that for me, that actually has been more relevant experience than doing calculus, 1 year earlier, right? Even though I went into math, the idea that I can just sit down, go on a video and be like, hi, I have a bit of screen presence and I'm a clear speaker and everything, this is what you need in interdisciplinary science. And I think that is very underappreciated. So I think that, there's some things I would change about the school curriculum. I think, definitely focusing a bit more on linear algebra and coding in high school could be very helpful, just so that way everyone could be at least conversant in it, even if they don't go that direction. Everyone's going to be touching a computer in their life, right? That's unmistakable. So at least knowing a little bit about what a for loop is or something to, is helpful. But I do think that, the world is getting so complicated that communication is more important than, I think it's, you want to specialize in something, do it very well, and you want to be able to communicate well. And if you can do those two things, then I think I think that you're much better off than trying to be, trying to learn every discipline out there under the sun.
But if you want to be a scientist, machine learning would be a great tool for that. Machine learning, programming in Python or Julia, because I know that you are a founder of a Julia community. Am I right?
I'm not a founder of the Julia community, though. I came in a few years later and wrote a whole bunch of packages. So now some people kind of, you might be able to put an asterisk on there at this point. I don't know. But yeah, I think that I think that there is something that could be done around. I mean, machine learning is going to be pretty prevalent for all of our lives in the near future, and I think that there should probably be something in high school curriculums or something like so that way so people understand what machine learning is and what it's capable of, right? I don't think that it requires going into the math to be able to describe it. Yeah.
Right now, people don't understand it. They don't understand the difference between algorithm and machine learning and machine models. Yes, really. So there is a need to talk about it. To talk about it.
Yeah. And I think that a very good educator can probably come up with a high school curriculum that's like, okay, like let's do machine learning in practice. Like, I don't know if it's something like, putting down some like beads or something, like some interactive thing with the class or something where they're moving around the objects by hand and kind of seeing the algorithm as a learning algorithm, right? So I don't know, maybe you can construct something where like, it's like, okay, if you so you have a classroom of individuals and you're trying to teach them an algorithm to be correct, right? And maybe you have some individuals that lie half the time and other individuals are always true. And you get to see and then you say, okay, is this a red bead? So they put their hand up or hand down, and you start doing check marks or something, and then you just start showing people like, okay, so who in the classroom do you trust, right? Maybe this person, and then you then come up with an algorithm from that where you're like, okay, my algorithm for finding out whether the bead is blue is whether this person, and this person raise their hand, right? You can probably construct a nice scenario like that and be able to teach someone like, hey, this is how a learning algorithm works without any mathematics really involved. And I think that that's the kind of thing that we will need in the near future because not everyone will need to know the math. I mean, I know that everyone in machine learning that's doing it, they're going to pound the ground and say, okay, everyone has to learn this math because it's the most important thing in the world. I think it's impractical, right? But, everyone, but for lawmakers, future lawmakers, future people who are political scientists and stuff, they should have a working understanding of machine learning. And I think that doesn't require a mathematical thing. It just requires that we ourselves understand it better to be able to teach it better. So.
Another quote from them is Hasabi's, and I'm curious how you would relate to that. That mathematics is the language of physics, and with biology being not so structured science as physics is, machine learning is the language of biology.
Ooh, I'm not sure I'm going to agree with that one, because I mean, I've worked a lot in this mathematical systems biology kind of area, and very similar mathematical principles are seen all throughout biological systems, right? So in biological systems, you can model these chemical reaction networks, and then when you model these chemical reaction networks, you begin to see that they're mathematically similar to things like signaling structure. So the same thing that you see in these kind of devices that are used for audio engineering and music and such, right? The same underlying electrical circuits exist in signaling pathways inside of the body. So one of the things I actually worked on for a long time was understanding zebrafish hindbrain, right? Understanding how the development of this hindbrain works, which is an interesting question, because if you think about chemical reaction systems and putting chemical, if you put a drop of dye into water, you see that it doesn't move as like a perfect circle, right? There's a lot of randomness to it, but somehow inside your body there is a chemical signal that starts here and it goes all the way down, and when it hits a certain concentration, your body knows, hey, this is where I stopped my arm from growing, right? And it works so well that both of your arms are the same length for essentially every person on Earth, right? So so biology, it looks like it's completely random and everything, but what we find when we look at it is we look at it and we see, oh, there's an electrical circuit under here, and if we look at this electrical circuit, if we look at this signaling diagram, its signaling properties are actually very similar to a low pass filter or a denoising circuit, right? And not even just similar, they're like almost mathematically identical to the things that we build when we're trying to make that guitar have less distortion, right? Like, so as someone who has done a lot of audio engineering and all this kind of stuff, playing with music, I actually found that when you started looking at biological systems, they really have the same mathematical pieces going on under the hood. Now, I think the thing that's interesting about it is, biology wasn't designed to do it, right? There is no designer of the system. And what that really means is that you don't necessarily have the assumption of modularity, right? So when you think about the things that we build in as humans, we normally think that, oh, if I build a chip, like a computer chip, I have an adder piece and I have a multiplier, right? There are different parts of your CPU that are doing different things. In a biological circuit, they're not necessarily different, right? Basically you have all these computational devices within your DNA, the transcriptomics and everything, but they're not necessarily modular. They're kind of overlapping in a way that is very beautiful and a bit more efficient than what humans would ever build, right? There's no reason why we need so many transistors in the CPU. If we reuse some of them to be the adder and multiplier together, maybe we could have done better, right? And biology finds solutions like that because there's no requirement in biology that it's human understandable at the end of the day. So we do find that it is a bit more complex. And that the assumptions that you can model every little piece separately is not necessarily true. But when you do begin to open it up and look at pieces, you do find that a lot of these same mathematical principles that you would use in electrical engineering, mechanical engineering, all these kinds of engineering spaces, they actually apply to biology, and you can really understand them at a biophysical level. So I mean, I will say that there's a lot that we don't know, and I mentioned early on that there's so much data out there that that we probably need machine learning to help us come up with better models, right? But I don't think that we should drop the models. I don't think that it's just all pure black box machine learning. There is so much that you can learn by trying to build a physical model of how different parts of biological organisms are working.
Let's get back to Julia. Could you shortly describe us, let's say, what Julia is?
So the Julia programming language, its core premise is that you can write things as simple as Python and have it run as fast as C, right? And the key behind that is, when a lot of people are doing this development, if you look at major Python libraries, you look at SciPy, you look at NumPy, you look at AstroPy, and all these kinds of things used in science, you see that there's a Python wrapper over some C or Fortran code, and the reason why that's done is because Python is just not fast for doing the actual computing, right? And so what Julia is as the language is something that solves that problem. How do you get performance out of high-level language? And because you have that performance, now you don't need to have two languages in your project. You just have these one, and you can then make use of that in various ways. So that's the high level of the language. There's a lot of other details in terms of, it's not object oriented, it's built around multiple dispatch, and there's a lot that we can go into, but the core behind it, the why behind it, is really to solve this two language problem and not have to require a fast language that you don't like to use, like C, plus a slow language that you like to use with Python, right? Instead trying to have a fast language that you actually want to use, that's dynamic and has all these interactive features, but it actually hits that same speed that you would expect out of C and Fortran.
Is it a difficult language to learn in comparison to Python, for example?
I don't think it's difficult. No, I mean, I think that there are some factors involved here, right? I think that one of the interesting things is that because of the lineage of object-oriented programming from Java, you have a lot of folks who have already learned object-oriented programming, and so when it came from time to go from Java to Python in the first CS classes, right? I was still taught in the Java times, and I'm sure that there are people way beyond me that learned in the Lisp times, right? I know that a lot of people learned at MIT. They used to always use Scheme in the first class, right?
Java is a huge ecosystem. That's why it will never die.
Yeah, but I learned it in Java times, right? When your first class is always Java, and then C++, and then everything else, right? So the transition to learning something like Python was like, oh, it's also object oriented. I just don't have to worry about putting my types here, right? Like there were just some things that it just seemed like it was like, oh, this is Java, but with less syntax, right? and so Python has this kind of lineage then that I think that makes it so that way it seems a bit easier to teach because of that lineage, right? And I think that with Julia kind of starts from a different spot. It starts from a Lispy heritage and multiple dispatch, right? I don't think that that's any inherently more difficult to learn, but I think that because everyone has been teaching, object-oriented first, then, you kind of go, okay, well, now we're going to learn some things in a functional style or, in an imperative style with multiple dispatch. If it's the second style of computing that you learn, you're always going to feel, at least to people who are just starting on learning it, right? You're going to feel like, oh, I feel a little bit more comfortable with object-oriented programming, right? And you see that with the Julia community, right? A lot of people come to it, they hear multiple dispatch and they go, well, I know object-oriented programming, so how do I do object-oriented well enough, and et cetera. And I think that the thing that's interesting here is that, the multiple dispatch, this difference is pretty core to the language. It's the way that you get the optimizations, the way that the JIT compiler is able to make things faster is actually because of multiple dispatch. So it's not like it's just like a choice or something. It's not like it's just like what about just doing the object-oriented version of it, right? It really is kind of core to the language. And so you do kind of really need to get the most out of Julia, you do need to really sit down and learn how to write things in a multiple dispatch style. But with all that said, multiple dispatch does have many advantages. In fact, I think the best way to describe it is actually not done by someone in the Julia community, but actually Bjorn Straustrup, the developer of C++, right? He actually he has an old paper, I think from the 90s, where he says, oh, making C++ object-oriented was a mistake. We should have done it with a multiple dispatch style. And he really describes it, right? You can think about multiple dispatch as essentially a generalization of object-oriented programming. So if you do object-oriented programming, you do like a.b, to be able to add, you might call the function a.b, a.b parentheses, and then you give it arguments, right? And really what that's saying in there is it's saying like, a is something special, right? So if I know the type of a, then I know what this function will be, right? And so you can have, a.b versus c.b can be different functions, even though they're the function b, because you're spacing it based off of a or the object a or c, right? And now when you start to do multiple dispatch, instead you're talking about, okay, I have a function f, and it could be dependent on the type of the first argument or the type of the second argument. So multiple dispatch, then you can do anything with object-oriented programming by going, okay, I have F and I specialize this function based off the type of the first argument, which is A, and then other arguments, or I have F, which I specialize the arguments based off of the type of C, other arguments. And so now I have a function F, which changes its behavior based on whether you pass in A first or C first, right? So it's like you move from A dot B, to now being F of, A or C goes to the first argument, and then you put other things. So in terms of like a syntactic change, it's like a small swap, right? Once you understand it. But the power of it is that now there's no priority given to the first argument. Basically, you can now dispatch and say, okay, I want the function that I'm calling to be dependent on what the type of the first argument is and the second one, right? And so there's no. And so it's a very flexible type of style that kind of supersets object-oriented programming, which makes it so that way there's kind of you can really flow between different styles and of, no dispatching versus single dispatching versus multi-dispatching. But of course, if people have already learned an object-oriented style, they come to it at first and be like, okay, how do I do A.F, right? And you're like, oh, no, just do F of A. And, but like, and it'll take a little bit to get there. But I think once you really learn it, like once you've tricked your mind into it, it's like, you're like, okay, this might actually be easier. I kind of think about it as, it's like kind of like learning like different human languages, right? If you're like, okay, the first time you have to learn a language, you're going to start by, if you learn a language that's kind of foreign to you, right? You keep one of the things that you really notice from people is that they keep the same grammatical structure that they're used to, right? So an English speaker is very used to, subject, adjective, verb, right? And so, when they go to another language, like Japanese or something, you talk with the same sentence order and everyone looks at you funny, like kind of understand you, but why are you saying it like that? And I think that with learning a language that has a very different paradigm like that, you run into that where, it's not necessarily that the paradigm is any harder, right? It's just Japanese versus, English and such, right? It's not that, it's just that you come from having learned a grammatical structure and you're going to impose that grammatical structure on everything that you do until you really begin to learn the language. And then once you really absorb the new language, you kind of start to use the structures and then you go, oh, okay, this is the easier way to do these things in this language, right? And then it kind of works out. But I do think that there's in this gap in the learning process because of it.
Yeah, but to learn Julia, you need solid foundations in object-oriented programming. Yeah, or
you really don't, because it's not a object-oriented programming language, right? You do need to learn some things like, if you know things like for loops and array-based programming and such, you're good to start. And then really, I think the key is that, I think it might actually be easier for someone to learn if they never really learned and internalized object-oriented workflows, right? Because object-oriented workflows start to tell you like, oh, I do this, and then I do composition, and and then when you go to Julia, then you go, well, we don't do object-oriented and we don't do, and so, so I do think that, if like probably the first half of a CS course is the same, right? We're going through for loops, while loops and everything, but then like CS 101 would kind of split at right there and say, okay, it would look more like if you're doing like a scheme or functional programming type of course, rather than doing an object-oriented one, which people used to do, right? People used to be taught that way in the CS 101. The classic first CS course at MIT used to be a scheme course, right? But now it's always Python and object-oriented learning. And so, it's just the expected lingo that everyone knows object-oriented programming first. And so then you kind of have to learn that, hey, object-oriented is not the only way to program. In order, it's kind of like learning your second language for the first time, right? You have to learn that, hey, these things that you've taken for granted as like the way that all sentences look like is not always actually true, right? And so then there's a bit of a brain fuzz you have to come over to do that. Either, I think that people either do that by learning, Haskell or learning Clojure or, Scheme. A lot of people who come to the Julia community have learned another one of these languages first. And so they're like, oh, I get it. There's different structures that can be done. I think that some people who've only learned, Python and R before, jump into Julia, they go, wow, this I've never seen something that's not based off of object-oriented, right? And that's really a bigger barrier there.
Do you recommend to learn Julia as a first language, not Python, when we think about machine?
I really do. I really do. And the reason is because with Julia, you can really see what's going on, right? I think that, you know, I have this lecture that I give. It's the second lecture that I give in the scientific machine learning course, which is how does serial code work, right? Which is this kind of this top-down view of, okay, you know, it starts with everything. It goes through everything from how is memory allocated to row major computations versus column major and everything, right? And one of the things that we do inside of this course in this section lecture is we show people that, you know, so that Julia is a JIT compiled language. So therefore, we can actually look at the assembly and look at the LLVM level of what is the code that we're executing, right? And I think that that's very interesting because, you know, for a lot of languages like R and Python, people really don't know what's going on under the hood with the execution, right? You learn the abstraction layers and you go, okay, I know that, you know, the plus works here and then but, you know, if you're to ask them, okay, so, you know, how is this actually working on your computer? Like what is it actually calling under the hood? You know, people just don't know, right? You know, it's like there's a Python interpreter and it does black magic and I get a result back, right? But if you see, or, you know, you could inspect the generated assembly, but then you're teaching everyone C, which is kind of difficult to do in its own right. But I do think that there are some advantages of starting with something grounded like C or Fortran. But Julia kind of hits this nice middle ground because, you know, we can do things like, you know, add to arrays and then go, okay, now let's inspect under the hood. What did it actually do? And you can start to see things like, oh, if I do C equals the array A plus the array B, well, what it has to do is it has to create a new array that it creates a new array and then it runs a for loop that is then adding the values into this array. Well, what if I wanted to, you know, make my code faster? Do I need to create a new array? Well, if I had another array around, I could write into it instead, right? And so if you start to show people what's happening under the hood, they can start to build up understanding of the abstractions, like what did I not think about that was going on in this computation? And how is that actually affecting my performance? How is that affecting correctness? How is that affecting all these different things? And so I really do think that, you know, with Julia, you know, Julia is still young, so it's kind of difficult for it to be there. But I do think that Julia is a language because it is so open as to how it's doing its computation. It shows you every little bit about how the LLVM works and everything, right? I do think it makes it a very nice teaching language because you can, you know, tell people, okay, you know, you write things very simply and things work. But as you go through the course, you can start to show people, and like, let's lift up the hood. You know, what does LLVM look like? Okay, you know, LLVM is this low-level intermediate language, and we see that we're creating an array here. Okay, and we see how type inference works. We type inference fails. Why would it fail? You know, how do types work? You know, and they can even go to the lower level. Okay, how is this compiling on my Mac versus on my Windows machine? Okay, so this is telling us that ARMv7 has different registers, you know, different cache sizes, and you can see all of that just from some simple inspection things. So that turns out to be, yeah.
You feel the machine, I would say.
Yeah, you can feel the machine. Now, at the end of the day, I assume that, you know, not every student's going to walk away from that and know how to like intuitively walk through it. But I do think that having that as like a very early lecture, like, you know, I do that. I do this in a graduate course, so I kind of assume that they've already learned how to program. So I do this as an early lecture. I think that if I was to do it in like an undergrad course, I'd make it a much later lecture, right? But I do think that when people walk away with that, they speak about their computation differently, right? They think about things like, oh, you know, I'm not just doing A plus B. I'm doing a memory allocation. And then I'm putting the results into the new temporary array, you know, and once you start to understand your code at that level, right, then, you know, once you understand more about what's actually being done, then you can understand like, oh, how will this affect how I do parallelism? How will this affect how I do, you know, and I think that, you know, a lot of people know how to do this because if you learn from C or C++, or, you know, you're forced to do this, right? You're forced to allocate every array. You're forced to do all this, right? But now that people are kind of being taught at high level languages, they kind of just don't know that all this stuff is happening, right? They don't even really know what allocation is. And so Julia kind of strikes this nice middle ground there, right? I mean, it strikes this nice middle ground because of solving the two language problem, right? But I think that importantly in teaching, when it strikes this middle ground, it abstracts away the Python, to the Python level. So it looks similar to the Python, but then you can ask it, hey, what's actually going on in the hood, and see the C++ style, right? See that and so that's where it kind of hits this middle ground that I think is, interesting then from a teaching perspective.
Yeah, that's great.
What does Julia have to do with Formula One?
Say the last part again.
What does Julia have to do with Formula One?
Oh, so Julia Hub, we as a company, right? So Julia Hub is a proprietary company. A lot of the creators of this company are also the founders of the Julia programming language. It was started, about half a decade later, as a way to try to figure out how to make a commercial entity that can keep a lot of people working on the language, right? And so one of the things that we really developed was this Julia Sim, which is a modeling and simulation platform. If you know things like Demola or Simulink, it's in this world of simulation, of modeling and simulation, with block diagram, composable types of forms, right? Now, one of the groups that we've been working with is the Williams Racing team, right? So in the Williams Racing team, they've been one of our customers. In fact, we have the Julia Hub logo on the halo. So if you actually watch the race, you actually see Julia Hub on there. And so one of the things that we've been working on them with is, if you can do faster computation, can we improve the models that are being used trackside, right? So as you watch the Formula One race, right, there's an engineer that's like on the headset with the driver that's telling them things like, oh, when you take this turn, instead of doing it at 40 degrees, do this at a 42 degrees, that's going to be a more optimal trajectory, right? So what we've been working on with Williams Racing is improved models, so Gaussian process models, a type of digital twin generated through some scientific machine learning tools, right? We've been working on these things to get new, more accurate models trackside into this trackside loop, so that way they can have more precise information on optimal trajectories and things like that.
Great. We will link it to the show notes, the website, because you showed us the website related.
Yeah. So this case study just went up like 2 days ago. So yeah, I mean, someone could check out the case study. There's some animations that aren't on a case study, so we'll probably be talking with the Williams Racing team to get some more animations up on there. But yeah, I mean, it's pretty exciting because I think people could see the Julia Hub logo on the car for the last year, but I think a lot of people had no idea what we were working on them with, right? So informally, I was telling people like, oh, there's finite element models for how the tire works. But now there's an approved case study. If you want to kind of see the different projects we've been working on them, you could go check out the website. So
last question on my part. You have some experience with pharma. What is currently the role of machine learning in drug development, and can we, let's say, do it with relatively small models and small computational power?
Yeah. So let me kind of give a broad overview of the space to start, right? When we talk about the drug development pipeline, right, there's kind of there's kind of a split in the middle of it. There's this early phase, which is called, generally that's what you call the drug development. And then you have this later phase, which is like the clinical analysis and clinical pharmacology, right? I'll say that almost all the work that I've done is in the clinical analysis and clinical pharmacology side, not in the drug development side, right? Though there are a lot of people who are using machine learning in the drug development side. So I'll say that, a company to look towards is Schrodinger, which is doing this for mining protein databases. There's a lot of things going on with molecular dynamics and DFT, and we could have a different discussion on that, right? But most of what I work on is not actually that phase, right? And so what is the difference when you talk about the drug development? That's saying, okay, I want, if I assume that I know that I want to have a protein that binds, let's say I have this protein, I see that there's way too much of this protein whenever someone has a given disease. Well, what I might want to do is I want to design a protein or some molecule to bind right here that makes it so that way this is now inallocated. Now it's unable to bind to other things because I grabbed the thumb, and so therefore, it fixes the disease, right? So the drug development phase assumes that we know what we want to bind towards, and then it's really about making protein compounds or molecules that can do this kind of operation, right? Now, what happens is, okay, once we have this, once we have such a molecule, that doesn't mean that we have a drug yet. We have a potential drug, right? And this is when you'll get a lot of flashy headlines. But there's a whole process beyond that is the clinical pharmacology. And what the clinical pharmacology is really about is, can we find ways to be able to administer this to people in a way that is both safe and efficacious, right? Both at a safe level, non-toxic, but at the same time at a high enough degree such that it actually affects and fixes the disease, right? And so there's different stages of this. So like the handoff point between the drug development pipeline and the clinical pharmacology space is quantitative systems pharmacology, known as a QSP. And what people do in QSP is you use very early studies on things like mouse and non-human primates is the word that a biologist will use. Most people think monkey, but non-human primates is the word. And what you would do at this at the QSP stage is you'd use the data that you have to answer the question of is this drug target actually viable for a clinical trial? Which is actually a much deeper question, right? And I mentioned before that biology is very tricky. You don't have this modularity. This is the reason why that really matters, right? So, and I think a nice study case to look at when thinking about this is the amyloid beta hypothesis in the amyloid beta hypothesis so the amyloid beta hypothesis in Alzheimer's disease, right, is the idea that amyloid beta is like somehow the trigger to Alzheimer's, right? And the reason why this is a major simplification, right? But the reason why this was looked at as the potential target is because if you measure an Alzheimer's patient, you'll see that amyloid beta levels are much higher. So if you always see that this protein is expressed way too high inside of this patient, then it's like, oh, this must be very much related to disease, right? And so for a long time, what people thought was, okay, if amyloid beta is high whenever we have someone with Alzheimer's, then let's develop a drug that inactivates or breaks down amyloid beta. If we can bring it down to the right levels, then we should have fixed the disease, right? It turns out that there are still ongoing debates about the amyloid beta hypothesis, but I think at this point, a lot of people are kind of seeing that, just thinking about amyloid beta as Alzheimer's is not correct, right? And the reason is because biological circuits are tricky, right? So, if you have, A turns on chemical, if A binds to the DNA, which causes B to be built, and if B binds to the DNA, which causes C to be built, which then causes amyloid beta, amyloid beta now causes A, right? If they're all causing each other, just simply decreasing one piece here won't make this chain go down, right? You'll end up having these kind of feedback factors that makes it that way. Oh, if you decrease the amount of amyloid beta, your body just creates more of it, right? And so, really understanding the biology at a circuit level is what's required for doing quantitative system pharmacology correctly, which is one of these reasons why I'll say that it's not just a machine learning problem, right? As a call back to earlier. But once you understand these circuits, you can begin to ask these questions about like, okay, if I do decrease the amount of amyloid beta, will that have any real effect on the end system, right? And you can then begin to see, like, oh, maybe this actually won't have an effect, and I need to, dose somewhere else, right? Now, the reason why this kind of comes later in the stage is because you need to have some kind of data to be able to construct these biological circuits, and do all this process to be able to then, once you have the circuits, you can start to see, like, do you expect this to work? And so this kind of comes after you have a bit of the molecule, but this is the stage before the clinical trial. So this stage only really started to exist, I think it's like 2012 or so, that you started to have these pharma companies start to do this quantitative systems pharmacology. But now it's pretty standard for a lot of clinical trials to have this kind of QSP prior analysis, basically understand, do we believe that the clinical trial is going to work, or do we believe it's not going to work, right? Based off of this kind of targeting study, or should we get some other prior data to really understand? So the QSP preclinical domain is one space I've been working a lot in, because I mean there's a great place right there where you have to come up with models, but the model can be very different for every disease. And so the process of doing, physics, where we came up all the way to general relativity, took humankind 400 years. We're like, okay, so how can we do that to understand Alzheimer's disease at at the Newton's level, but let's do this in a 3-month period, right? That's where, people are doing a lot of mathematical modeling by hand, but now machine learning assisted mathematical modeling is kind of this key piece that's kind of helping there, right? But that's the preclinical stage, right? Once you have something that says, okay, we think that this is actually a viable drug target, now let's actually go to the clinic, right? Phase 1 of clinical trial starts. Then you have this question of, how do I know what dose should I even be giving to people, right? And should different people be dosed differently, right? So males and females might respond differently to a drug, or you might be weight dependent, right? And what you then do there is you do something called nonlinear mixed effects modeling, which lets you kind of learn how different individuals will react differently to a drug, to then be able to learn how to optimize the dosing regimens across the population. And that's then the that's like the core of clinical pharmacology today. So it's all, I want, once again, I mean, this is all differential equation models. It would, it's very similar to the types of models that you'd see in physics, which are now being used to model drug dynamics within the body. The drug dynamics in the body in a way that's patient dependent. And then when you get to the other side, you then have, optimized dosing regimens for the population. You hope and pray that enough people, are efficacious without it being toxic, and there you go, you have a drug, right? So I do think, the reason why I'm bringing this up is he said, drug development, and I do work in the drug development pipeline, but I work in this pharmacology space, which is kind of after you would have thought the drug is developed, but how do you actually administer it correctly, and will that work, is kind of two questions that have to be addressed at that point. And it has a lot of mathematical things going behind it. So
I only wanted to say that it is awesome what Chris said, and it's this knowledge about it is not very popular. So I think people don't know how it works with clinical trials, with drug development, and with the use of machine learning and mathematics in the whole process. So I wanted to sum it up.
Yeah, I do think, I mean, not many people really know that pharmacology is really even a thing, right? It's kind of it's like a kind of unknown discipline outside of the field. But yeah, there's a lot of people that are doing, I mean, the models are differential equations. So, it's very similar to the models you'd see in like physics and biophysics and stuff, that are really kind of used to be able to come up with the prediction on your pill bottle of, that you should take this dose, or it should be different depending on your weight and such, right? That all comes down to biophysical models that people are building. And so, but once you know that, you can go, well, okay, if we have all this stuff going on in scientific machine learning that's helping you build models, wait a second, are people now using machine learning to help build these models of how dosing should be different? And that's precisely what's going on. So there's a lot of exciting stuff going on here.
Chris, thank you so much for having you on the channel. It was a huge intellectual pleasure, and I hope it is huge intellectual pleasure for all the audience. It's always great to talk to scientists and see, let's say, how machine learning can be applied to science. Fascinating topic. So a big thank you.
Yeah, and thanks for having me. I'm always happy to go on the kinds of things. They're always fun, and this one was fun as well. So thank you for having me.
Thank you so much for listening to Sherpa Search on Tech. If you have enjoyed the show, please subscribe to our show wherever you listen. Thanks again. The Sherpa Search on Tech podcast is a production of Sherpa Search, an executive search firm specializing in the tech industry, helping hire the right people for expert and managerial positions, and advising how to build and develop long-lasting, high-performing IT teams. If you would like to learn more, reach out to us at maciej.szczerba@sherpasearch.tech or visit our website sherpasearch.tech. See you next time.